Here we go. Specific heat capacity. So, how much heat in kilojoules is absorbed for 1.45 kilograms of iron to heat up from 21 to 85.4. So, this wasn't the best color I picked here, of course. I just imported it and it didn't do a very good job. But, okay, how much heat? So you guys can copy this down. I'm going to go quickly, so keep up the pace here. 1.45 kilograms of iron. Specific heat capacity of iron is 0.449 joules per gram degrees Celsius. And the temperature change, of course, remember, it's the final minus the initial. So 85.4 minus 21. Delta T here, of course, don't forget, is final minus initial. So it could be negative, it could be positive. Keep that in mind. This is 85.4, so that's a difference, 64.4 degrees Celsius. Okay? That all works out to be a positive 41.9 kilojoules, and that is how much energy is required to heat up that chunk of iron in this case. Okay? Good? Okay. Next, we need to write out a balanced chemical equation using delta H notation for the formation of magnesium carbonate. So magnesium plus carbon plus oxygen gives me magnesium carbonate, solid, balancing. Let's see, 3 there, 2 there, 2 there, 2 there. We need to use delta H notation as well. Thermochemical, balanced chemical, thermochemical equation. You're going to look up the heat of formation for magnesium carbonate. So delta FH in your data booklet is a 1095.8 kilojoules per mole. We're making 2 moles here, so we're going to times it by 2. Okay? And our delta H notation right there would be delta H is negative 191.6 kilojoules. Okay, at the end there, balanced thermochemical equation. Okay, 2 magnesiums, 2 carbons, 3 oxygens, magnesium carbonate. All right, moving on. Next, communicating enthalpy changes. We need to do a decomposition and a term within the equation. So decomposition, term within the equation of hydrogen iodide. So hydrogen iodide, which is a gas when you look it up in your data book, H2 and I2, gas, of course, 2 of those. We're going to look up, once again, this is for decomposition. So in your data booklet, you'll look up delta FH. Delta FH for this particular one here, HI, is a positive 26.5 kilojoules per mole. We're not doing formation, we're doing decomposition. So I'm going to do delta DH, okay, which of course is a negative 26.5 kilojoules per mole. I'm decomposing actually 2 moles in this case, so I'm going to multiply it by 2. And of course, I'm going to put that, because the decomposition is a negative, it's exothermic. Because it's negative exothermic, I needs to go on the right-hand side of the equation. So therefore, over here, I'm going to put plus 53 kilojoules, because that is how much energy I'm getting out of this system, yes? Okay. All right. Communicating enthalpy changes. Let's see here. I got to make sure this all matches up because a few of these are different. Okay, it looks good. We're going to draw and label in a potential energy diagram for the combustion of ethyl cyclohexane. So, and we got to do a combustion reaction, and there's the delta CH for it. So we're going to draw a potential energy diagram. First things first, probably should write out potential energy diagram. Of course, includes reactants and products, delta H, etc., etc. So we need to write all that stuff out. Ethyl cyclohexane. Here we go. Good review. This is how we're going to combine all this stuff together. There's cyclohexane. Ethyl means we have 2 carbons added on, CH2, CH3. Okay, that's C8H16. Don't forget, there's 2 there. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes? So that is the formula you'll get from that. Plus oxygen gives me carbon dioxide. and water. Balancing it, I think 8's and 8's there, and a 12 there, if I'm not mistaken. Okay. They tell you that the delta CH, the combustion, heat of combustion for this reaction, is a 2125.6 kilojoules per mole that I burn. I'm only burning 1 mole according to this balanced chemical equation. So once again, if I was writing delta H notation, I'd say over here, I ran out of room, of course, as per usual, I'd say a negative 2125.6 kilojoules, yes, is what I'd do there. I'm going to do a potential energy diagram. Okay, well, potential energy diagram looks something like this here. All right, so potential energy, kilojoules, the reaction coordinate, basically, you know, time usually is something we put there. So you're going to start with this graph, high or low, exothermic reaction, negative, high or low, high, the correct answer. So we're going to put our reactants here, we're going to drop down a little bit, products there, yes? C8, H16 plus 12, O2, gas. And we're going to release delta H here, negative 2125.6 kilojoules. And I'm going to get 8 carbon dioxide, 8 water, gas. What your potential energy diagram should look like there. Yes? Good? Questions? Anyone? Endothermic, of course, start low. You got to put energy in, so you got to increase the potential energy, and then you get your products. Yes. Don't forget which one of these is the most, has the most potential, obviously, or the most has the most potential. Of course, it's the reactants in this case. And then once you burn it, of course, you're losing potential energy. Yes. All right. Moving on. Good. Go calorimetry. We love calorimetry. In calorimetry, don't forget, you're going to be talking about energy gained and energy lost, right? So we got 1 point, actually yours is 1.30, mine's 13, so mine's a little different, but that's okay. We're going to go with this one here. This is what you guys got, 1.30, yeah? Yeah. And I think the rest of the numbers are good there for me, I believe. Yeah. So, okay. And we need to calculate delta solution H. So don't forget, these ones, it's been a while, obviously, so that's why we're reviewing. We got E gained here, and we got E lost. What's gaining energy in this question? Look at it. What's gaining the energy? Hurry. Water. Yep. What's losing the energy? What's giving that water energy? Yeah, magnesium chloride is being dissolved into water, right? When you dissolve magnesium chloride into water, it gives off energy. That energy is being taken in by the water. Well, water, I can figure out how much energy was consumed by using MC delta T, of course. Pretty common for water, yeah. And then on this side here, if I knew how many moles I used, don't forget the negative there, I could figure out the solution, the molar enthalpy of the solution. Okay? So we're going to, on that side, of course, we're going to do delta solution H. And we need to figure out how many moles we have. So we have, let's see, on this side, 1.30 grams of magnesium chloride. Molar mass is 95.21 grams per mole. And I'll calculate delta solution H. On this side, we have 75 milliliters of water. Don't forget, if we're doing 75 milliliters, if we're doing these types of questions, we want to convert it to kilograms because kilograms and kilojoules go together, right? So don't forget, 0.075 kilograms of water. Specific heat capacity is 4.19. I'm going to cheat a little bit, not going to put in the units there. And the temperature change is a rise of positive 7.80 degrees Celsius. Calculating for all that stuff there. Okay, I'm not going to skip. I'm going to skip the math just for time's sake here. Delta solution H is going to be a negative 179.5 kilojoules per mole. And once again, we'll use significant digits, etc., etc. I mean, basically that's what you should get. So -1, I guess we should say negative 180 kilojoules per mole. Delta solution H. Okay, is what you'll end up with there. I think it's 3 significant digits. Ultimately, you guys will figure that out. Okay, not a big deal. All right, moving on. Good? All right, next. What do we got next here? Oh, yeah, mixing 2 solutions together. I like this one. Oh, yeah. All right. They talk about, first of all, they give you the milliliters and the concentration of hydrochloric acids mixed with 300 milliliters of excess sodium hydroxide. So they're telling you you have too much sodium hydroxide. So that basically by default means that this here is your limiting reactant, right? How much energy I can produce is based on that alone, because once that runs out, I don't have any more hydrochloric acid left to react with the sodium hydroxide. So once that runs out, that's it. So that is going to tell me how many moles of solution I'm using, or basically how much energy I can produce if you want. Okay. Now yours is a little, let's see, mine's a little different, right? So I might need a little help with this one here. My number's a little different right there. That's okay. So once again, you have to ask yourself, what's giving off the energy? What's taking in the energy? What's gaining energy? What's losing the energy? What's gaining the energy? What is it? What's gaining energy in this one? Huh? Yep, water. Temperature of the water is going up, guys. Solution goes up. Temperature of the water goes up. What's losing energy? Yeah, hydrochloric acid, right? What about the sodium hydroxide? Well, that's the excess. Don't have to worry about it. I got lots of that stuff. The HCl completely tells me how much heat I can get out of this, right? So we're going to do delta solution H, I think they told us, because we're just mixing the solution together. Or neutralization, maybe it is, right? Whatever, doesn't matter, same thing. Delta solution H, delta neutralization H. I don't remember what they want in this one. Over here, I need MC delta T for the water, of course. Okay, water is the only thing that's getting heated up there. So what do we need to do? Well, we need to do over here C times V, yes? So N in this case here works out to be, where did I go here? About 0.0535 moles. Okay, and we're going to find delta solution H or delta neutralization H. I honestly forget which one's which. Okay, so one of those two. Okay. Next, I'm going to do MC delta T on this side here. How much water do I have? 300 milliliters? 250, right? We got 300 and 250, so that's a total of 550, right? Don't forget, you're mixing the two solutions together, so a total of 550 here, kilograms. 4.19, of course, and the delta T. What does the delta T work out to be for this one? Like I said, mine's different, so 6.8, yeah, that's it, degrees Celsius. Okay, when we solve for all that, let's see, delta solution H or delta neutral, I forget honestly, which I guess it's probably neutralization, isn't it? And delta solution or delta neutralization H works out to be a negative 292, yeah? 293 all said and done, kilojoules per mole, okay, is what you should get there. So, calorimetry. Not only do we have a fuel here, 1.85 grams of 2-methylpentoinine, we got 150 gram copper calorimeter filled with water, okay? So, and we need to figure out delta CH for this one. So, what we need to do in this case here is, don't forget, we need to talk about energy lost here, right? Energy gained. So N delta CH in this case, and on this side here, not only do we have the copper pot, okay, so that's part of it, we also have the water. So we're not only heating up the water in this case here, okay? And once again, this is for copper, this will be for the water, okay? This is basically that, if you remember back to the experiment we did with that, we had that aluminum pot there kind of thing, and we heated up both, okay? So, here we go. Well, let's fill in the left-hand side first here. Unfortunately, I definitely did not leave enough room for this. We have a 150 gram pot, that's 0.150 kilograms. Specific heat capacity of copper is 0.385. Okay, and the temperature change, of course, is 18.50. And I also am going to include, of course, the water. The water was 275 milliliters, so 0.275 kilograms. Make sure you change it to kilograms, guys, or at least at the end if you do that somewhere, okay, because that way you're going to get kilojoules as an answer. 4.19 is a specific heat capacity, and the temperature change, of course, we have to assume it's the same. If we're heating up the pot 18.5, the temperature, the energy is going to go to the water 18.5. And on this side here, we need to figure out N. We don't forget we got a negative there. So grams per mole and delta CH here. And we need to figure out delta CH, of course. What do we got? 1.85 grams. And we have this for 2-methylpent-1-ene. So pent, right? 1-ene, like that, 2-methyl, CH3. So we need, what, 2 there, that's got 4, that's got 4, that's got 4, that's got 4. Okay? The formula for that works out to be C6H12. Okay? The molar mass of that is 84.18. So we can fill that into there. Okay? We can calculate delta CH finally. All right? So remember, this plus this divided by all of that stuff there, yes? So that all said and done here, delta CH should be a 1019 kilojoules per mole is what you should get for that. All right? I'm not going to do all the calculations for that, but that's what you'll get. Okay? It's actually 1018.5 or something like that. And I know it's significant digits. You guys can worry about that later. Yep. Yep. Okay. So that's not significant digits, obviously, and that's okay. It'll say record your answers 3 or 4, obviously, as usual. So no worries there. Straight there is fine. Okay. So that's that. Good. You don't need an equation for that one. Okay. You obviously should be able to write one out, but you don't need one for that. All right. Another calorimetry one here. Here we go. Okay. Okay, this one here says, what is its heat capacity of the bomb calorimeter? Bomb calorimetry is a little bit different, don't forget. This is all good here, I think, so let's move on to the bottom here. Bomb calorimetry, okay? Don't forget, E gained here and E lost. You do have a fuel in this case. The fuel, of course, is this funny-looking pentan 1-all here, so we'll talk about that in a second. It does have a molar enthalpy of combustion. They tell you that, and you use 4.88 grams of fuel. So I'm going to burn that fuel. How many moles, I don't know. We'll figure that out. And what do I have on this side? Well, it's a bomb calorimeter, so don't forget it's big C delta T. Because remember, bomb calorimeters have their own specific heat capacity, and it's measured in kilojoules per degree Celsius. And basically this question here, they're asking you, what is C? That's what they want to know. What is this bomb calorimeter specific heat capacity? So if I'm going to do that, this is all the stuff that I need to fill in there like so. Okay? If I want to get C by itself, basically. I didn't do it that way in last class, but no biggie. All right, let's see. So I have 4.88 grams of fuel. I need to, I might as well fill this in here. Negative 3330.8 kilojoules per mole is the delta CH for that question. It rises by 12.4 degrees Celsius. So that's my delta T. I need to find out the molar mass of this. So pentan 1-all looks like this. Pentan 1-all. Okay, this will be 3, 2, 2, 2, and 2, I think there, yeah? 2 there. So that formula there works out to be C5H12O. Okay? C5H12O. And I can use that for the molar mass now. 88.17 grams per mole. And when I do all this, calculate big C here, when I calculate all that out, be careful what order you're doing this in, and obviously all said and done you'll get 14.9 kilojoules per degree Celsius. Final answer is what you should get for that. Okay. Good? Yes? All right, next. Hess's law. Oh yeah. We need to basically rearrange these so that we get the final equation at the bottom, right? Our target equation. Don't forget when you're doing these, okay? Once again, look for the major stuff. Don't worry about the elements. Don't worry about the little stuff like CO2s and things like that. If you see CO2 on one side and you see CO2 somewhere else and CO2 somewhere else, don't worry about that because that's probably going to cancel out in the big scheme of things. Worry about the major things that you see here. I need some N2O3 on the left-hand side. Here it is right here. I got one N2O3, but it's on the wrong side. So I'm going to flip it. Okay? So I'm going to put here, flip. So that turns out then, therefore, delta H, I know this isn't going to show up very well here. Maybe I'll cross that out. Negative 83.7 kilojoules, right? If I'm flipping the equation, I got to flip the sign, yes? Remember? Okay, so that's taken care of. That's on the right side now. I have that on the left-hand side. I need one NO right here. And look, I have that on the right side, but I got two of them. So I'm going to divide this by 2. Yes? I'm going to take equation number 2 and divide it by 2. That'll give me, what, 90.2? And same sign, of course. I don't change the sign. 90.2. Okay, so I'm not going to use that anymore. All right? Good. Now I got this done, right? And now I look for the last one, NO2. Oh, look. Perfect. This one, it's on the right-hand side. Good. Leave this one alone. So I'm just going to use the positive 33.2 there. Add them up, right? You don't have to change anything with the numbers. You already did the numbers. Add them all up, and you'll get final answer here. Delta H is a positive 39.2. Okay, done. All right. Good. Once again, focus on the major things here. Don't worry about look at all this stuff here. That's crazy, right? If you start trying to balance all that stuff out, it's going to take you forever. Look at the major stuff. Now, does all that other stuff cancel out? Well, I hope so. I pretty much guarantee it does, but I didn't check it. So, you know, keep that in mind, right? I'm pretty sure this is all good here. It's got to be. Because in order to get that equation there, I have to do that to each one of those. It's set up so that everything else has to cancel, right? If you're forming something, that's part of it. It's gonna work out, trust me. So you can go back and check it whenever you get some free time there, but I guarantee it'll go. Okay? We've done Hess's law, so I think I'm just going to give you the answer for this. If that's okay. You guys know delta H equals the products minus the reactants, yeah? Just to save a little time here, guys. Sum of the products minus sum of the reactants. Okay? Delta H in this one here, if you get a little free time and you're not sure, if you don't know how to do this, then obviously try it. But remember, don't forget, you're going to look up CO2. You're going to go 4 times CO2, 6 times H2O liquid. Don't forget, 2 times the, what is that, ethanol. And then oxygen, remember, is an element, so we don't need to worry about it. All said and done here, you'll get a 2733.6 kilojoules answer. Remember, it's only in kilojoules because you are calculating the molar, or sorry, the enthalpy for that particular reaction. Okay, so just kilojoules there. Okay, good. Like I said, check it out if you're not sure. Make sure you use the right water. That one's liquid. So when you're looking here, that's a liquid, of course. Don't forget to use the right number for that. This will be in your data booklet. That you don't need to worry about because it's an element. It's 0. And of course, look up carbon dioxide gas. Okay, heats of formation. All right, moving on. Oh, thermal stability is always a good question. Always, always, always. Most stable to least stable. Well, the first thing you need to do here, okay, is you're going to look up delta FH values for those. Okay, you're going to find delta FH. That's if you wanted to form it. Thermal stability basically means this: how much energy is required to break apart that compound, right? How thermally stable is it? In other words, how much, like I said, the more energy it takes to break a compound apart, the better it sticks together, right? The more stable it is. So we don't really need to look at delta FH. We probably need to focus on delta DH, the decomposition. So that's the first thing you need to do with this question. You need to convert all those formations into decompositions. So like I said, this will be data booklet, okay? Data booklet there, and you're going to convert them all to delta DH. So here we go. Let's see. For KCl, SO3, CH3OH, and SNO2. Here's the numbers. This is for, by the way, delta DH. Okay, this is positive. They're all positive, by the way. 436.5, 395.7, 239.2, and 577.6. Okay, are the values for that. Those are all positives. All right, they're all positives. That's how much energy is required to put into them to break them into their elements. Okay, that's how much energy is required to put it into this compound to break it into, for example, potassium and chlorine. So most stable to least stable. Most stable, of course, requires the most energy because it sticks together the best. So SNO2, most stable. KCl, next stable. SO3 next, and CH3OH least. And this is the most. Okay? Most stable to least stable. Okay? Good? Yeah. Okay. Switch a sign. Yep. Okay, a little bit of stoichiometry here. 2 more questions. Yeah. Well, I think we can get this done. Okay. Let's see, is that the same one we got? Perfect, yep. Okay, so this shouldn't take too long here. Geez, I really wish this would have converted to a different background, but that's okay. All right, well, let's see. First things first here. It says, oh, that's a balanced chemical equation, and that's how much heat you get out of it, right? Now remember, right here, well, maybe I should write that down real quick. Just bear with me here. Okay, so that's the equation you guys have there. Remember, what they're telling you is that if you burn 2 moles of this product, you get 4163.2 kilojoules of energy released for every 2 moles. Well, you're not burning 2 moles, okay? In fact, I don't know how many moles we're burning. It says here we want to release only 500 kilojoules of heat. So I want this to be 500 kilojoules. Well, remember, you can do this in a formula way. You can just do a little common sense. I don't care how you do this. You can do ratio proportion if you want. That's really what the formula does for you. But if delta H equals N delta CH, okay, we could figure that out. Okay, it says here I want to release 500 kilojoules of energy. Okay, how many moles would do that if I have a molar enthalpy of negative 4163.2 kilojoules for every 2 moles that I burn? That's my molar enthalpy of combustion for this particular fuel. Okay, so you can solve for N here. N will turn out to be positive, of course. Okay, and I'm going to save a little bit of work here. That works out to be 0.240199 moles. Okay. The molar mass of that, 86.2 grams per mole for this right here. Okay, so I have N and I have big M, of course, and I multiply those two together, and the mass that I would have to use here is 20.7 grams. Okay, would be your final answer. Now, there is definitely other ways to do that. Okay. We're not going to have enough time to go over, anything else, but you can do ratio proportion. I don't care, but you need to figure out how many moles of that you're actually burning to get the 500. Once you know how many moles you're burning, which is like 0.24, then you can use that with the molar mass to figure out the mass of that fuel that you're burning. Okay, and the last one here is efficiency. Okay, efficiency. Let's see, does this match up? I really hope so. Sure. looks good. Calculate the tank's efficiency. So once again, if I burned 220 grams of methane and I heat up 70 liters of water from 8.5 to 43.7, calculate the tank's efficiency. So this one just does a percent yield, percent error kind of thing here, how efficient it is. Remember, the lower number always has to go on top with efficiency because we can't have anything that's more than 100% efficient. So maybe what I'll do is, let's see. If I did, well, let's put it this way. Let's say, I know you can't see this really. If I did burn 220 grams of methane, I guess the question is, how much heat would I actually get out of this? Because remember, we know how much heat is actually going to be absorbed here. It says to heat up 70 liters of water, et cetera, et cetera. But if I burn 220 grams, and I use the molar mass here, which is, let's see here, 16.05. I know you can't really see that. Maybe I'll just move it to the bottom here. So if I did burn 220 grams, and the molar mass was 16.05 grams per mole, sorry, that's an N there, I would get, what, 13 moles burned. So if I actually used that 220 grams of methane, that's equivalent to about 13 moles. Well, 13 moles, if I wanted to figure out basically delta H for this, I would take N delta, what, CH, I guess, right? So if I wanted to figure out the heat that theoretically should be produced from burning 220 grams of this fuel here, I would take that times the molar combustion, molar enthalpy of combustion. So look, 802.5 for every one of those, right? So basically I'm going to multiply this by negative 802.5 kilojoules per mole that I burn of methane. And that gives me 11, well, I might be a little bit off on that number, but it's about 11,000 kilojoules. That's probably rounded to something a little bit there, okay? So that's 11,000 kilojoules. Theoretically, that's how much energy I should basically be giving off, okay? That's how much energy would be given off theoretically based on 220 grams of methane. However, it does say at the top here, you heat up 70 liters of water from 80.5 to 43.75. Well, how much energy actually was used in that? Well, we can use Q equals MC delta T in that case. Look, the mass of water is 70 liters. Well, that's 70 kilograms. 4.19. So how much energy did it take to heat that up, right? And we're going from 8.5 to 43.75, so that's a difference of 35.25 degrees Celsius. And Q in this case works out to be, all said and done, 10,338 point, et cetera, kilojoules. Okay, I'll just end it there. It's close enough. You got the idea. So apparently 10,338 kilojoules was used to heat up that water, but theoretically I used 11,000 kilojoules. So we can calculate the percent efficiency, right? Always the smaller number over the larger one. And of course, if you multiply it by 100, that just changes it to a percentage, right? It's basically percent yield, percent error kind of thing. And if you do that, it works out to be about 94% efficient. Okay? All said and done. All right. I know that was kind of quick, guys, but those are some of the questions that, like I said, I'll podcast that, and hopefully it worked out. And if it didn't, well, you know, at least you'll see the work, if nothing else, worst case scenario. If you have any questions, you guys come see me, et cetera, but that's kind of the stuff that, some of the types of questions we looked at in Unit 1, which I realize has been a long time ago. So, you know, key formulas, things that you need to think about. Q equals MC delta T, delta H equals NC delta H. MC delta T twice if you're heating up a copper and some water, aluminum pot with water in it. Bomb calorimetry, C delta T, okay? All those things is all things we need to consider there.